Hello friends, welcome back after a long break. Today we shall be discussing new method for design using PBD approach. So it is unified performance based design. We shall discuss the theoretical background of this method and we may take one or two small numericals. Final application will be taken up in new video. So why this method is required? Because the existing other methods, which is the direct displacement based design method, can accommodate only one design objective at a time, and that becomes a handicap. To overcome this limitation, this method has been devised. So where from the name comes, the term unified performance based design UPBD was coined by Choudhury in 2007 in his PhD thesis titled Performance Based Seismic Design of Hospitals. It was first applied in frame shear wall buildings, and later on in 2013 it was applied for RC frame buildings. However, the method has been applied so far for steel buildings, bridge piers, water tanks and other cases. We shall take up gradually these cases in our coming videos. So what are the design parameters as objectives we want to satisfy in performance based seismic design? These are interstory drift, which we have discussed. It is actually the ratio of the sway between two adjacent floors divided by the height of that floor. It can be expressed either as ratio or it can be expressed as percentage. Another is the plastic rotation, theta p, and the plastic rotation will give you the performance level of the member or of the system. Which plastic rotation value corresponds to which performance level, these are available in FEMA documents and ASC ACI 41 line documents. You can also have strain as a parameter in design objectives. You can have also have crack width as a parameter. Out of these, the first three I have seen so far been dealt upon for PVD to accommodate these three. The last one is important, but I have not seen any performance based seismic design philosophy accommodating crack width. So direct displacement based design, which we have already discussed in terms of the frame buildings and in terms of the frame shear wall buildings in our earlier videos. It is the limitations. What are the limitations? The method itself was good. It was directly giving us the design displacement, and based on this, using the displacement spectra, we could design the building to achieve our targets of drift. But the limitations are like this. It takes only one parameter, one design objective, then the drift, and it cannot accommodate the performance level, which is very important to declare the performance level of any structure. So you cannot decide the performance level of a structure for only drift. So that becomes a serious limitation of this method of DDBD. Then it does not suggest any initial member sizes. So if the member sizes are not given through the theoretical approach, the designer remains in the wilderness and he has to go by iteration. So before you arrive at your required sizes, which gives you the target design drift, you may require many iterations and it will be prohibitive in design office. So let us see the advantages of the UPBD method, the unified performance based design method. It can accommodate two design objectives, namely drift and performance level. Since it unified the two parameters, drift and performance level, that's why the name was given as unified performance based design. Other advantages is that it can give the member sizes in the beginning of the design, and as such you don't require iterations. Almost iterations are not required to achieve your design objectives. So there is a great advantage in design. Then it has been found that these buildings designed using UPBD method are more economical than the corresponding coral buildings for the same performance levels. You consider certain drift, say 2%, you consider performance level, say LS, and your coral building gives you this kind of performance, and find out the cost of that building. Now you use UPBD method for the same performance objectives, and you will see that it gives lesser cost. So that is great advantage. Then UPVD buildings are less fragile. If you carry on the fragility analysis, you will see that the probability of damage of the UPVD buildings are lesser than the coastal buildings. UPVD buildings have less damage index. So damage index we may be taking up in our coming videos sometime. Less damage index means less damageability of the building. So UPVD buildings are less damageable than the coastal buildings. So if we have so many advantages, why not use this method for performance based design? So that is what we want to learn. We will see the theoretical background and we will see simple applications. Let us see what is the effective stiffness. This we have perhaps discussed in earlier videos also in connection with other items. We have here a base shear versus roof displacement response of a building. Initially it is linear, and if it is linear, the stiffness is called initial stiffness Ki. Then gradually after yielding it becomes non-linear, and in any point on the non-linear part of the curve, if you want what is the status, what is the stiffness, then you have to join the origin and this point. The slope of this line joining origin and the point concerned is called the second stiffness, or also known as effective stiffness, given by Ke. So A is the point where the performance point has been achieved in the base shear versus roof displacement curve. This point here corresponds to the target displacement delta D, which is also known as the displacement at the performance point delta PP, also sometimes written as target displacement delta T. So you are designing a system for this displacement at this level of damage state of the response curve. Now let us see further the performance point and the performance levels, which this also we discussed earlier in some references. So in the base shear versus roof displacement curve, you have the IO damage state, you have the LS damage state, and you have the CP damage state. Now you have a performance point where the reduced demand and the capacity of the structure are identical. So this is the ideal point where it should be designed. So displacement at this point is delta PP, displacement at the performance point, and we want to design for this point only. Again here we have shown the Ki and Ke. As we have seen earlier, the distance between the IO and LS is called damage control range, and from LS to CP is called limited safety range. Now how do you know whether your building is a life safety building or immediate occupancy building or collapse prevention building? For that purpose, you have to locate the IO, LS and CP after carrying out the nonlinear performance analysis, namely pushover analysis, and also identify the performance point through the methods given at ATC40, which we have discussed in our earlier videos. Now you see the relative position of the performance point with respect to IO, LS and CP. In the current figure, the performance point is here and IO is on the left hand side of this performance point. So it indicates it is a IO building. Now suppose we consider a building which is having a location here, say near LS or after LS. This building has the performance point on the left hand side of the nonlinear curve, so that building will not be LS building because it is beyond performance point. LS is beyond performance point, CP is beyond performance point. So in the nutshell, you can say the level which is encompassed by the performance point immediately on the left hand side is the performance level of the building. Suppose my performance point comes here, then immediately on the left we have the LS, so it is the LS building. If the performance point comes here after CP, then immediately on the left is the CP point, so your building will be called as a CP building. Now let us see the plastic deformation dictating the performance levels. Again we have taken the response for base shear versus roof displacement. It is a response which is initially straight line, then becomes curvilinear after the yield point. So here is the yield point. Corresponding force is the yield force yield base shear, and corresponding displacement is the yield displacement. Now yield displacement and maximum elastic displacement are the same. So here you can say either it is elastic displacement from O to A, or you can say it is yield displacement. Beyond that, the displacement after the performance point here, after the point B, is the plastic deformation or plastic displacement delta P. So delta D is O to B, delta E or elastic displacement is O to A, and plastic displacement is A to B. Same thing we are now taking in terms of rotation, not displacement, because in most of the FEMA documents our performance levels will be dictated by rotation of the members and not displacement. So if it is rotation, corresponding force is moment, so it is a moment rotation response. So at this point you have the yielding, so it is the yield moment My, and corresponding displacement here at A, which is the yield displacement, which we have written as delta E, elastic displacement, maximum elastic displacement delta E or yield displacement. Beyond this point A, whatever displacement or rotation is visible here are the plastic rotations. So this is theta P, plastic rotation. So obviously theta D consists of theta Y and theta P. So that is what is written here, theta E equivalent to theta Y equal to theta YF for a frame. Okay, this elastic displacement theta E, which also could have been written by theta Y. So it is equal to theta Y here, and for the frame we write it as theta YF. This is the practice. So with this understanding, let us see the Upbd method of RC frame building. The source is like this, Choudhury and Singh, 2013. Name of the paper is A Unified Approach to Performance-Based Design of RC Frame Buildings. Journal of Institution of Engineers, India, Series A, May 2013. Volume 94, page 73 to 82, and the DOI is also given here. Now if you want this paper, original paper, I can supply you the copy. You write to this mail and I can supply. Because for understanding Upbd method, this was the original source file, first writing, so you must read it. Now let us see what is the theoretical background, how it is developed. Here is a multiple degree of freedom system. It has so many beams and columns. These moment resistant frames. Now this can be converted to an equivalent single degree of freedom system, as we have discussed in our previous videos. This equivalent single degree of freedom system, ESDOF system, has a single mass, effective mass ME, has a effective height HE, and other properties like effective stiffness, etc. we'll see. Now this single degree of freedom system is swaying on one side. The total amount of sway in terms of angular rotation is theta D. This is your design displacement in terms of, or design rotation, and as you know, rotation can be talked in terms of the interstory drift ratio also. So this is your design drift, theta D is your design drift. So total rotation is the design drift. This rotation consists of the elastic part, which is we have seen earlier, theta E or theta Y, or also known as theta YF. F stands for frame. So this part is elastic, and next part of the rotation is plastic, theta P. So with this understanding, we can write theta D equal to theta YF plus theta P. Now if we have the expression for theta YF, then we can proceed further in the formulation. Theta P is the plastic rotation which is available from the FEMA documents or ASC SA 41, corresponding to any performance level of your desire. So we start with this equation, theta D equal to theta YF plus theta P, which is we are writing as equation number 1. And the value of theta YF is available in the literature by Priestley 2003. It is 0.5 epsilon Y LB by HB. So let us say this is equation number 2. In this equation number 2, the epsilon Y is the yield strain. So it is Fy divided by ES. ES is the modulus of elasticity of rebar. LB is the length of the beam in the direction considered. HB is the overall depth of the beam. So this equation 1 and 2 are combined now, and we get theta D equal to 0.5 epsilon Y LB by HB plus theta P P, the theta P is the plastic rotation. This theta P plastic rotation will arise out of either columns or beams in the frame buildings. Now columns do not fail because we carry out the capacity design so that the only beam fails. So this theta P plastic rotation, I can tell that it is the plastic rotation of the beam. So we are designating this by theta PB. So this equation 4 has been rewritten here, and now we transpose the sides and take this part on the left hand side. So theta D minus theta PB. From this we can find out the value of HB. So HB equal to 0.5 epsilon y LB divided by theta D minus theta PB. So this is your $1 million equation which gives the depth of the beam. What is the peculiarity of this equation? This equation is giving depth of the beam, so now you need not search for the depth. One dimension of the beam is known, but this dimension is arising out of two parameters of the design, the drift and the performance level, because the plastic rotation of the beam will dictate the performance level of the system. So this depth is now accommodating the drift and accommodating the performance level of the building. So this is the beauty of this equation. Now how to get the width of the beam, depth of the beam from this equation? Width of the beam is not a big thing. Generally width of beam is taken as 1/3 of the depth to 2/3 of the depth of the beam. So that can be easily obtained. Now question is how to get the column size. Column size you can get two ways. You do one thing, adjust the column sizes such that the percentage reinforcement in the column is 3 to 4%. This range is practical range of steel in the column. For example, Indian code gives the maximum range is 6%. At 6% the steel will be overcrowded. So this can be a practical limit of the percentage steel in the column. So if I maintain this percentage steel in the column, all the column become uniform with respect to its concrete size and steel size. So that is one way of getting the column sizes. Another way is given by this paper Mayangbam and Choudhury 2014, determination of column size for displacement based design of reinforced concrete frame buildings, in the Journal of Earthquake Engineering and Structural Dynamics, July 2014. So interested readers can see this. Now let us take up the equation that we have developed. The equation was HB, depth of the beam is 0.5 epsilon y LB divided by theta D minus theta PB. Let us make this dimensionless by transposing these sides, and we write it like this: HB by LB. LB we take on the left hand side, and right hand side is 0.5 epsilon y divided by theta D minus theta PB. This equation 2 here can be plotted for the parameter HB by LB ratio with respect to the design drift. What happens to epsilon y? If I take Fy constant for a steel, then epsilon y is constant. If I consider a particular performance level of the system, then theta PV becomes constant. So only variable here is the left hand side, and the right hand side is theta D. Value of theta PV for corresponding to performance level are available from FEMA documents or from SCI 41 document. Now how much the value of theta D in that equation you have to decide. In FEMA documents some hints are given for particle elements. Particle elements means columns, shear wall, etc. For IO, 1% transient drift with negligible permanent drift. LS 2% transient drift with 1% permanent drift. And CP 4% transient or permanent drift. Based on these hints, we shall consider the value of theta D ranging from certain ranges for IO, LS and CP. So for IO, we consider it is ranging from 1% to 1.5%. For LS, 1.5% to 3%. And for CP, 3% to 4%. Now question is what happens below 1%? Below 1% drift is very stringent, and this may lead to uneconomical design. So this has been excluded. So we start from 1% drift. So this is some sort of assumption we are making so that we are able to draw a curve for that equation. However, this assumption is not altogether imagination. These are coming arising out of the documentary evidence as given here. Now, plastic rotation are given in the FEMA documents, FEMA 356 for beams controlled by flexure. There is bending beams. The value of IO, LS and CP in radian are given like this. Now you see these values are given in tabular form in terms of the steel ratio. This tensional steel, compression steel and balance steel. So in terms of steel ratio and shear ratio. Shear force divided by BWD into root over FC dash. So this ratio are changing with respect to different members, and the transverse reinforcement is written here. C means compliant. So these are the buildings which are maintaining the ductile detailing. So these are called compliant buildings. So 4 cases are given for compliant buildings based on the steel ratio and the shear ratio. Now if you want to use exactly the value, say 0.010 for IO radian, then you need to find this ratio and this ratio, which is very difficult prior to design. So prior to design you do not know these ratios, these determining ratios to take the value of IOLSCP rotations. So what we can do is an approximation. We take the average of these 4, average of these 4 and average of these 4 for the value of plastic rotation for IO, LS and CP. This will lead to a little inaccuracy, but it is within the range of acceptability for normal design. Now with this concept we are drawing this figure for this equation, HB by LB ratio given by 0.5 epsilon y divided by theta d minus theta pb. So this for IO, what happens? It becomes HB by LB into 0.5, and we are taking say Fy equal to 415 megapascal. So 415 by 2 into 10 to the power 5 is this much, this ill strain of the rebar. And theta d is a variable, and theta pb is the value just we have seen in the previous slide for IO performance level. It was 0.00625 radian. So now you find this value HB by LB ratio for varying theta d. How long we shall vary? For IO we shall vary it from 1% to 1.5%, to here to here. So if you plot, you get this curve AB, following curve like this. Fine. Now we can use the same thing for again for LS. For LS, what will change? This numerator will remain same. In the denominator, this value will change, theta PB corresponding to the LS value. So if you change this and again you vary theta D will now vary from 1.5% to 3% as we have assumed. So we are assuming this range is within LS level of buildings for drift. So putting this, you get curve like this, which will be coming, it will come from here corresponding to 1.5% and fall like this and come and goes like this. So we are not interested in those parts because those are HB LB very high, of no practical use. So we have shown this part C, D. Alright, so this is the LS curve. So what does it indicate? That if we here at any point if I am, then I take the HB LB ratio here, then I shall get a LS building. You get it? I am here in a point in that LS curve CD. So corresponding vertical value is HB LB ratio here. So this ratio will give me a building which will be satisfying LS condition. Now see, this same ratio is also matching with the IO building. Okay, point was here. I have come here and this is HB by LB ratio. The same ratio will also give me IO building. So why should I go to LS building? I shall remain to IO building, which is a higher performance building. So this part of the curve which is shown dotted is to be discarded. So what we do, we draw a line, horizontal line from point B. What is the point B? The end of the IO drift, 1.5%. So from here, if you drop a horizontal line, wherever it is meeting this CD line, it is meeting at the point M, then MD becomes the value for LS level of performance. Clear? Otherwise it will not be economical. I shall be utilizing the same depth of beam for LS building, whereas I could already get a building of IO level with that depth. Alright, now let us come to CP curve. For CP curve, I shall change the value of this plastic rotation here corresponding to the CP performance level and find out this ratio again, and I get this curve here as shown. Here also with the same logic, any point here, suppose E corresponding to CP building, will be giving also LS building, and LS building is better than CP building, so why should I use this part of the CP? So this part of CP I do not use, so I drop another horizontal line from the point D. What is the point D? The end of drift for CP performance level. So if you drop a horizontal line and go up to the last point we have considered 4% drift. Beyond that, building may not be stable and it will be beyond CP. So we stop here. So we have got an upper bound curve which is encompassing all the performance levels. So if I am below this, in this zone, here to here it is IO. If I am in this zone from this point to this point, I am LS, and within this has portion from here to here, I get CP building. What is the green curve here? Green curve is the elastic line. Now we go back to the equation here. What is elastic condition? When that plastic angle is 0. So you put theta PB 0 and you get this equation HB by LB equal to 0.5 epsilon y divided by theta D. Obviously, varying theta D from 1% to 4%, I can get a line. So this is the line. This you can tell as the lower bound of the system, lower bound of the performance. So your building must lie within the Hess zone bounded by the upper limit and the lower elastic limit. Now question is, suppose I am in the LS zone of design, I want to have a LS building. So obviously in the LS building I can have a depth varying from here to here. Here HB by LB more, so means HB is more. Here HB by LB is less, so HB is less, so depth of beam is less here. So why should I not use a lower beam depth than the upper beam depth here? The thing is, if you use a lower beam depth, then that beam will not go to its full plastic level up to IO. So it is some kind of uneconomy when you are targeting IO or LS. Here it is LS, you are targeting LS, but the beam is failing only up to certain plastic level. You can also use a beam depth corresponding to the elastic condition. In that case, there will be no plastic deformation. You will not get so-called LS building. But the depth of beam is less, so economy you may get. So in that building may be very flexible. It will not be of any use to you in functionality. So in the nutshell, we can say we should target taking building at the upper bound level so that it is fully developing plasticity of the corresponding performance level. And obviously at any time you should not go below the elastic condition here. So I think this curve is clear. You have to refer to this curve because without this you cannot exactly select the beam depth. One can say that I can select the beam depth from this equation directly. You can use, but those logics are coming into picture, no? IO range, LS range, CP range, and the logic we have discussed why this part is to be discarded, why that part is to be discarded. So considering all this practicality and intuition, we need to have this curve also in the design. Let us take a numerical example so that it is clear how this scheme is working. So I've taken a question, find the beam size required for an RC building with beam length 6 meter for designing an IO building with drift 1.4%. Given Fy is 415 megapascal. So data given is LB equals 6 meter, performance level IO theta D 1.4% with 0.014 radian. Because drift can be expressed either in terms of angle or in terms of percentage, and Fy 415 megapascal. Now we need to have theta PV corresponding to your IO performance level. So from 356, theta PV equal to 0.00625 radian. Epsilon y, the yield strain of this rebar, 415 by 2 into 10 to the power 5 is this much. Now find out this ratio HB by LB from our equation 0.5 epsilon y divided by theta d minus theta PB. It gives you 0.134. Okay. Now you go back to the curve and see what happens to your 0.134 condition for IO to this curve. Our drift, you come to the drift was 1.4%. So this is 1.5%. If you divide into 5 parts, 1.4 will be somewhere here, and you come here and come to this level. This is my IO. So IO 1.4% drift corresponds to this point here, and this part you can divide into 5 segments, then 0.11, 0.14, 14, 1.13, 1.4 up to 0.15. So this 0.14 going vertically and coming horizontally, it seems it is coming around 0.13. Okay. So from the graph I get the value as 0.13, the ratio HB by LB. So HB equal to 0.134. It shouldn't be 134, it should be 0.13 into H, the length of the beam LB, so 0.78 meter. Now you round it, so rounding we shall do on the higher side, so it's a 0.8 meter depth of the beam, and the width of the beam can be say 1/3 to 2/3, so we have taken 50% here, 0.4 meter. So this is the suggested beam size which will be giving you a IO building. Targeted drift is 1.4%. An IO building. So simply you have to use this beam size throughout your building height, and you will get IO building for 1.4% drift. So easy now. You need not search, need not iterate. Simply use this dimension. Furthermore, you note this Upbd method does not require any specific skill of the mason, because a mason is already trained how to use a beam of any size. So he is simply using this beam size. If you are really making a building, the mason may complain that beam size is very large, because he is generally using a lower beam depth for 6 meter. However, for requirement of the IO and the drift, you require this beam depth, and you will achieve it. You know iteration will be required, no change of the size of the beams will be required. Let us take another example, numerical example 2. Find the beam size required for an RC building with beam length 6 meter for designing a CP building with drift 3.4%. Again, Fy is 415 megapascal. So here we have taken the same beam length to compare. So 6 meter, performance level is CP, theta d is 3.4 or 0.034 radian, Fy 415 megapascal. Theta PB for CP is 0.02 from FEMA 356 tabulation. Epsilon y is same as earlier. So this ratio comes out to be HB by LB 0.074. As previous case, you can go to the graph or let's go and see. Our drift is 3.4%. Here is 3.5%. So 3.4% is here. You go to the CP level and vertically you come here. It is just above 0.1 HB by LB ratio. You can take 0.11. So that is what we have taken, 0.11. So HB equals 0.11 into LB is coming at 0.66 meter. By rounding it, we have taken a size of 0.7 meter, and 50% of the depth we have taken as the width 0.35 meter. So this is the suggested beam size which will give you a CP building. Targeted drift 3.4%. This target satisfaction of IO, LS or CP or any drift is not possible in the codal design. In the codal design, the code may say, we wish your drift should be this much. For example, Indian code says the elastic drift should be 0.4%. That is the wish of the code only, but the code will not tell you how to achieve this, how to restrict your building to that value. So this is possible in this performance-based design, and this Upbd method, which is more robust, more versatile, which is accommodating two performance levels together and giving you the sizes also in the beginning so that you need not iterate for the sizes. Thank you very much we are carrying out the performance-based design with the intention that our community world over, not only in India, become concentrated with the performance-based design. The codal design have the limitations we have discussed in the beginning videos. They cannot satisfy any target set by the user. Also, they cannot design for arbitrary seismic level. The Upbd method we have discussed today, we have considered the sizes etc. which is targeted to achieve a drift and performance level. We have not considered till now, we have not discussed till now about the seismic level. You can achieve this under any seismic level. Any seismicity level 0.3G, 0.36G, 0.4G, whatever it is, you can satisfy and you can get this building designed as per the Upbd method. And finally, you can check whether the building is actually satisfying your requirement under that design level, design seismic level. So all these are possible in the Upbd method, and Upbd methods. Gradually, I feel the entire world will be changing, switching over to performance-based design. In SCI 41, certain things are already there, which are performance-oriented. Other countries are gradually converting their code partially. In Indian could say they have already taken the C by B ratio, they have accommodated, and a little here and there they have accommodated also the infill element as a start model. Thank you very much for coming with me up to here. We shall see in the next video with the application of the Upbd method for frame buildings and more videos in future. Please like the videos, share the videos, subscribe the channel and carry forward with me. You can put your comments and your queries in the comment box. I shall try my best to answer. Thank you.